Hello, and welcome to Astronomy 100. In previous segments, we were talking about solar and lunar eclipses, and we discussed the mechanics of why eclipses occur and the details of the eclipses themselves, the difference between a solar eclipse and a lunar eclipse, and we showed some pictures of what you would see if you were to experience such a thing. In this particular segment, we're going to wrap things up by discussing why eclipses are rare. So here's the idea. A solar eclipse requires it to be a new moon, which happens once a month, 12 new moons a year. A lunar eclipse requires it to be a full moon, which happens again once a month, and there are 12 full moons in a year. So the question is, if a solar eclipse requires a new moon and a lunar eclipse requires a full moon, and we have them once a month, why aren't eclipses something that happen all the time? Why are eclipses rare? So in this particular segment, we're going to discuss what has to happen to make eclipses be perfectly possible and talk a little bit about why eclipses are rare when things don't occur the way that they're supposed to. So the basic idea is that during a lunar eclipse and a solar eclipse, there has to be a perfect alignment. And the ability to have a perfect alignment is essentially not able to happen because of how the moon orbits the Earth. And as you can see in this particular illustration here, that the moon in its orbit around the Earth is actually tilted in its orbit by 5.2 degrees. Now this picture is a little bit tough to imagine, so you have to imagine that you're looking perfectly edge on. This white line that works its way across the screen is what we call the Earth's orbit plane. Essentially, the Earth is always halfway above and below this imaginary plane that includes the entire orbit of the Earth and also the Sun as well. The Moon's orbit plane is this yellow line that connects the Moon at two opposite places in its orbit. And you can see that there's a tilt of 5.2 degrees between these two orbital planes. Now, what that translates into is that there are times when the Moon is above the Earth's orbital plane, and there are times when the Moon is below the Earth's orbital plane. So I'm going to switch to a model to show you how this works. If we have the Earth, and the Moon represented by this styrofoam ball here, what we end up having is a rough approximation of their actual sizes, but what I'm about to show you is not accurate when it comes to their distances apart from one another. The Earth's orbit plane can be imagined as this flat line, flat plane that extends off in all directions halfway down from the center of the Earth through the equator, or more or less the equator, off 23.5 degree tilt. But the Moon's orbit is actually spending half of its time when the Moon is moving around the Earth above the Earth's orbit plane, and then it spends half of its time below the Earth's orbit plane. So you can imagine as the Moon continues to work its way around the Earth, it rises above the Earth's orbit plane, but then it works its way around and plunges below the Earth's orbit plane, and then comes back up through, and then it ends up being above the Earth's orbit plane. So what that means is that most of the time there cannot be a perfect alignment between the Moon and the Earth and the Sun, which is of course required for any sort of an eclipse to happen. Now what I'm going to show you is a picture that is to scale, meaning that the attempt to represent everything in this picture is to make the Earth and the Moon the appropriate sizes and the appropriate distances apart from each other. And admittedly, this is a tough picture because things are very, very small. When we try to make everything to scale, it shrinks everything down, and it is a bit tough to see, but I'll try to help you recognize the various parts of it. Here's the Earth, and if the Moon is the appropriate size compared to the Earth, here is the Moon. Notice how small the Moon is compared to the Earth. And the distance between the Earth and the Moon is appropriate. And the distance is about 250,000 miles between the two bodies. Here is the shadow that the Moon casts because of the Sun. And you can see in this illustration, the Sun is off to the left and the light is coming to the right. So here's the shadow. And here is the Earth. And again, the sunlight casting upon the Earth creates the shadow that the Earth has that extends off into space. Now, the 5.2 degree tilt is also incorporated. And what I want you to notice is that when the Moon in its orbit is at a point where the 5.2 degree tilt has the moon above the Earth's orbit plane, you can see that the moon completely misses the Earth's shadow, so that there's no lunar eclipse possible. Remember, the moon has to pass through the Earth's shadow for a lunar eclipse to occur. Likewise, when it is a new moon, even though we have the sun and the moon and the Earth lined up in a way to make it a new moon by definition, but what you'll notice is this 5.2 degree tilt has the moon below the Earth's orbit plane, and so the moon's shadow, even though it makes it the appropriate distance, it is falling short of hitting the Earth because of this 5.2 degree tilt. So normally what happens is none of the shadows basically intersect the object that creates the eclipse event. So this is typically what happens. So what you might be thinking is, then how do eclipses occur at all? Because when you put all this together, it seems like it's just nearly an impossible event. However, we do actually have several eclipses each year. So what I'm going to show you is essentially what has to all come together to create the alignment necessary to make an eclipse possible. So this next illustration will demonstrate that. And again, it's a bit complicated, but I'll explain it to you. So what we have here is just a partial view of the Earth's orbit plane. That's the gray section right here. And then what we have is the moon's orbit plane, which is the white section. Imagine we take a cookie cutter and we cut the Earth's orbit plane to just simply mimic the shape of the moon's orbit. The 5.2 degree tilt is shown here, and what you can see is that the moon is above the Earth's orbit plane, and then it passes through the Earth's orbit plane, and then now it's below the Earth's orbit plane, and then over here it rises back through and comes above. Where the two planes intersect is what is called a node. And it's just a generic term that means when two planes intersect, a place where they happen to intersect is called the node. If we draw a line through the two nodes, notice that there's one node where the moon passes through the Earth's orbit plane. There's another node where the moon passes through it once again. If we draw a line through the two nodes, this is called the line of nodes. Now, to make an absolutely perfect alignment occur, what we have to have happen are two things. The first thing is that we have to have the moon on the line of nodes. And notice that the moon could be in any one of these places along its orbit, but it has to be exactly on one of the nodes, and it doesn't really matter which one it ends up on, but it has to be on one of them. The second part is that the line of nodes has to point directly at the sun. So if the line of nodes points directly at the sun while the moon is on one of the nodes, then we get a perfect alignment between all three bodies. And although this looks possible, obviously with these illustrations here, let me show you all the ways that it could end up not happening appropriately. For instance, you could have the line of nodes pointing at the sun, but the moon could be anywhere in its orbit at that moment. So an example is if it happens to be a first quarter moon while the line of nodes are pointing at the sun, then the moon is right here, and obviously we don't get an eclipse. If the line of nodes are pointing at the sun, but the moon is a third quarter moon, or a waning gibbous moon, or a waxing gibbous moon, or a waxing crescent, is all sorts of places the moon could possibly be and not be at one of the nodes. So if you're thinking this through very carefully, what you'll recognize is that the moon is on a node twice every month. So regardless of whether or not the line of nodes is pointing at the sun, the moon has to cross one of the nodes twice, essentially once and then again twice each month. So that means that eclipses are essentially only possible twice a month at the very best scenario. But remember that you could have the moon on one of the nodes or on the line of nodes when the line of nodes is not pointing at the sun. So how often does the line of nodes point at the sun? Well, this next illustration will demonstrate that. And admittedly, it's a very busy illustration, but I'll show you the parts that are the important part. Here is the Earth's orbit plane. Now we're showing the entire portion of it that the Earth is always on as it orbits around the sun. Here is the moon's orbit plane. Okay, you can see there's a 5.2 degree tilt between the moon's orbit plane and the Earth's orbit plane. This is the line of nodes, and notice how the line of nodes in this instance is lining up with the sun, pointing directly at the sun. But when the Earth moves in its orbit, you'll notice that by the time the Earth moves over to this portion of its orbit, the line of nodes is no longer pointing at the sun. So essentially, the line of nodes points at the sun here, but it does not point at the sun for all of this, all the way through here, until the Earth returns over to this side, half an orbit later, and you can see that the line of nodes are now pointing at the sun. But then the Earth continues in its orbit and the line of nodes are no longer pointing at the sun. So essentially, there's only twice every Earth orbit, or twice a year, that those line of nodes are going to line up with the sun, but the moon may not necessarily be on the node at the appropriate time. So essentially, when you put all of this together, the requirements of where the moon needs to be and how rare it's going to be in that appropriate place, and the requirement of where the Earth needs to be to have the line of nodes point directly at the sun, and then have both of those come together simultaneously, is going to make eclipses a very rare event. Now, don't confuse rare with impossible. Eclipses are definitely possible, as we already know, we experience them. And because all of this orbital mechanics is something that happens with regularity, these are things that can be figured out and calculated in advance. So we now have the ability to predict when eclipses are going to occur, where on Earth you have to be, how long the eclipse is going to last. These are things that can be calculated in advance, and of course computers are very good with all of these number crunching formulas that have to happen to make this possible. So eclipses are rare, but not impossible, and they do happen with regularity, although it is not something that occurs every month because of how everything needs to come together. Now, to wrap things up, there's one final part that we need to talk about, and that is, how do we actually know what to predict ahead of time? And essentially, there are two things that you want to consider. The first question is, how do we know how long the duration of totality will last? If you recall from a previous segment, we talked about what the duration of totality is. And then the other thing is, how do we know where on Earth eclipses will occur? So both of these are numbers that can be calculated based on the mechanics of the eclipse and can be figured out ahead of time, and we do this quite regularly. And to show you this, here is one of my favorite pictures. This is a total solar eclipse, and it is a total solar eclipse that was visible over the continent of Antarctica. And so this person in this picture is essentially standing very, very close to the south pole of the Earth. And so it was only the very, very smallest part of Antarctica that was able to witness this eclipse, because the eclipse shadow was able to graze the Earth just barely over the South Pole. So the bottom line is any place on Earth, every place on Earth is able to see eclipses at some point or another. There's no place on Earth that's immune from eclipses. And then lastly, how do we know how to predict eclipses? Well, let me show you an example of this. What I want to show you is some information from an eclipse from a while ago. This was from 2008. And you'll notice that it is from February 7th of 2008, we had an annular solar eclipse. And you'll notice on the 20th of 2008, February 20th, we had a lunar eclipse. And so this seems as if it's a random event, but what you'll remember from a previous segment is an annular eclipse is when the distance between the Earth and the moon is quite large, making the moon appear rather small, and it makes the sun and the moon combination to where the moon can't completely cover the sun. So we had an annular eclipse, and if you recall, what we're going to have is a lunar eclipse when we have a full moon. So this was the new moon of February of 2008, and then the next full moon that we had a lunar eclipse. And the reason is because the line of nodes was still pointed at the sun for this set of eclipses to occur. But then you'll notice that many, many months go by, still 2008, before we have the next set of eclipses. We have a total solar eclipse that occurred August 1st, but then again, 2 weeks later, when we have a full moon, we have a lunar eclipse. So these things seem random, and you can imagine that if you were living in a society quite some time ago, you would be scared, you would be alarmed by what you see. The event is something very dramatic, and because they seem to be completely unpredictable, it would be something that would be quite frightening. But today, eclipses are completely understood. We understand what is going on. We understand what is necessary for an eclipse to occur. They're predictable, so they're not frightening anymore. And now eclipses have become something that we enjoy and in some cases make an effort to go and take part in. And I hope you will too someday. If an eclipse happens near you, in your neighborhood, make a point to go out and see it. I think it'd be something you'd enjoy. That's about all the time that we have, and I hope you'll join me next time.